how to get to Earth from Mars. My name is Casey. My day job is running Terraform Industries, which is a synthetic fuel startup. And I thought initially I'll get super technical with this crowd, and then I thought, let's just bring it back to basics and see what we get. Now I find that kind of the getting back to Earth, having got to Mars, is often underestimated, even though it's by far the hardest of the 3 steps. And this is why it's well, this is how it's done. So broadly speaking, orbits are ellipses with the sun at one focus. And Mars's orbit and Earth's orbit are basically non-negotiable, but the black orbit, which there corresponds to a transfer orbit, is kind of free choice. And the key thing is, I kind of wish I could point at these, but there's 2 of them. The key thing is that the ellipse has to be roughly tangential at Mars's orbit and at Earth's orbit, so that when you launch, you can do physically possible things with rockets. And then you follow this kind of trajectory, and it takes between 4 and 6 months to get from one orbit to the other. It doesn't matter which direction you're going. This graph doesn't have arrows on it. That's basically how it's done. And for those of you who like to Google things, it's known as a Hohmann low energy transfer. Yeah, and unless you have some sort of antimatter rocket, you're kind of stuck doing something like this. And then there's an additional complexity, which is that Earth and Mars's orbit are not in the same plane. And so if you're very unlucky, it will turn out that the best time of year in which to do this launch, because of course, you can launch from Earth anytime you like, but when the black orbit takes you out to Mars, you really hope that Mars is there waiting for you. It might be that you also have to do some horrendous plane change maneuver, which, depending on your desired landing date, which ends up costing a lot of energy. Anyway, so the good news is you don't have to solve this by hand. It's known as the Lambert algorithm. And I think I also had impulse and no-birth effect here. To good approximation, all the thrusting is happening very close to the Earth, right? So it's called the trans-Mars injection burn, happens effectively in low Earth orbit, and then nothing much changes, you're just coasting the rest of the way until you slam into Mars, going at about 6 to 10 kilometers a second, depending on details. Yeah, so you can solve this by hand, but you can also just use a computer. And if you do that, it's quite straightforward to make a graph like this, which I made a while ago now. I might have to redo it because we're getting to run out of time. And so on this graph, what we have is what's called a pork chop plot, which is a map of the amount of delta V that you need to fly either from Earth to Mars, that's above the line, or from Mars back to Earth, and that's below the line. On the horizontal axis, you have years. So we're in 2024 right now, and that corresponds to Mars year, I can't read properly there, 37 or 38 or something, Mars year 37, towards the end of Mars year 37. And yeah, and then if you pick your launch date and then translate vertically upwards until you run into a bluish section, and then run down with the gray diagonals, and that'll tell you when you land. So the transit time is on the left-hand side of the graph there. It's ideally 6 months is kind of a long time to be in space. 2.5 years, much longer. And then there's one additional detail, which is that this graph includes only trajectories in which a swing by of Mars results in a free return to Earth. So you're able to come back to Earth, and if you decide not to land on Mars for some reason. And then the color map, if you like, is given in the top right-hand corner, which gives the amount of delta V you need in excess of the amount of delta V you need to get to orbit, to get from low Earth orbit or low Mars orbit back to the other planet. And so blue is ideal because that's the minimum spend. To get to low Earth orbit on Earth is about 9.3 kilometers a second of delta V, and on Mars is only about 4 kilometers a second of delta V, which is one of the reasons why it is possible to fly from the surface of Mars all the way back to Earth in a single stage, which is the observation that motivated the development of the Starship, pictured on the right, an absolute mammoth rocket. And then on the left here, we have the amount of cargo mass you can transport as a function of delta V at burnout. And that assumes a couple of features there given on the right, which will make sense to people who spend too much time thinking about this. But the long and the short of it is that if you need something like 7 to 7.5 kilometers a second of delta V to fly from Mars back to Earth, then you can take about 100 tons of cargo in addition to a 100-ton dry mass of your Starship. And of course, Starship today is nowhere near 100 tons dry mass. It's much more than that. So there's obviously work to be done in Starbase. No pressure, guys. But you'll also notice that while it is possible for an unladen Starship to fly single stage to orbit on Earth, that's about 9.3 kilometers a second on the far left-hand side there, the actual amount of cargo it can take is minuscule. So that's why they use a two-stage system with the Super Heavy booster on Earth in order to launch significant amounts of cargo into space. which is a neat trick. Here, let's see how we're going for time. Here is a chart that I wrote up a while back based on the book The Martian by Andy Weir, which he wrote almost 10 years ago now, maybe 15 years ago, but closely based on work that NASA had published on their kind of ideas for how to get to and from Mars. And you'll notice it involves about 6 different space vehicles, multiple different launch vehicles, lots of different transfers back and forth, all kinds of mission-critical operations and so on here and there. You need a nuclear-powered deep space propulsion system. Obviously, there's something for Orion to do there. And for all of this, you get something like 30 to 60 days on the surface for 4 people at the cost of, well, with SLS baselining cost, we're talking like $1 trillion. Unfortunately, and in contrast, this is the SpaceX concept, or the current version of the SpaceX concept for launch to space, or launch to Mars or to the moon, which involves multiple launches of the world's largest rocket. That's the hard part, down in the bottom left, in order to refill the Starship in low Earth orbit, at which point it can fly to Mars, refuel on the surface using in situ resource utilization and some power source, and then fly all the way back to Earth. So there's only one deep space capable spacecraft. There's only 2 key impulse motions. The first in low Earth orbit to go to Mars, and then the one from Mars back to Earth. A much simpler system. And for the same $1 trillion, you could probably put several tens of thousands, if not hundreds of thousands of tons of people and stuff on Mars, which is nice. This is what my company is doing. So we're actually making synthetic natural gas from sunlight and air for applications here on Earth. But it was inspired initially by running the math on doing this on Mars. And as of earlier this year, we've actually done it. We've made pipeline-grade natural gas from end-to-end demo. That's one of our older test rigs there in the picture. It's just a very nice picture. So feel free to come and ask me questions about that later. And yeah, that's into backup slides. So 7 minutes. Thank you.
Cool. Questions?
Questions?
Thanks, awesome.
Yes.
How close are you guys to a system that would work on the Martian surface?
You would want to re-engineer it from scratch, but we will be the world experts in it.
Obviously, it's useful on Mars. Is it useful on Earth to be doing the Mars technology for Earth stuff?
I really hope so. Spent 3 years doing this. The argument basically goes that if solar power gets cheap enough, it becomes cheaper to turn solar power back into fuel than to turn fuel into electricity. And depending on how fast solar continues to improve in price, this is going to happen by 2029. So now's the time.
Another question?
Yes, sir.
I saw a hand somewhere here. Oh.
So a lot of methods to create SAFs and other things require some really finicky catalyst that gets grumpy if you have power cycling, that sort of thing. How sensitive is this to constant power?
It doesn't care, which is the nice thing about just making methane. Yeah. Chris?
Anything specifically in the last 5 years that popped into existence, other than you, that makes this possible right now?
I think the success of SpaceX as a model for fast-paced, scrappy engineering is very inspirational to a lot of people in the sector.
Oh, those are fire answers.
Yeah, I'm trying to get through a few. I have 20 backup slides in case people want to ask me random questions about stuff. So anyway.
Yeah, go for it.
So this specific concept envisions essentially a one-all spacecraft. Are there advantages to actually having something closer to Martian-style architecture where you're able to have multiple different spacecraft that specialize in different things?
In my view, the Martian architecture answers the question, how do you get a few people to Mars and back once? And the SpaceX architecture answers the question, how do you get 1 million tons of stuff to Mars as quickly and cheaply as possible? 2 quite different questions with quite different answers.
Time for last question.
Yes?
How does your technology differ from solid oxide electrolysis and zeolite?
I actually have no backup slides on that. Our technology is we're basically trying to stake out the corner of the parameter space with absolute minimum capex, like maximum scrappiness. And thus far, it's turned out to be the correct approach.
Cool, you're at time. Thank you.
Okay, thank you.
That was the most questions in the shortest time.